Okay, for what we have in the crossover to Chapter 2, we have with matrix operations, and we'll be looking at various operations among matrices, and we have what the author has for the first theorem in the second chapter. Okay, say we have three matrices, A, B, and C, and we'll say that they will be of the same size, and let R and S be scalars, and and for what we have in this case, we're going to have the commutative property of addition as well as the associative property of addition. And we have also the zero property, respectively, with parts A, B, and C. And we have utilizing scalars, R and S. We had the distributive properties in sections D and E regarding matrices. And we have also what would be the associative property of multiplication in part F, and and we'll be looking at operations between matrices, especially in the case of working with multiplication, and we have by definition, okay, we have if we have that A is an m by n matrix, and if B is going to be an n by p matrix with columns B of 1 all the way up to B of p, then the product AB is going to be the M by P matrix whose columns are going to be going from AB1 all the way out to ABP. And I'm going to give some samples to kind of go from theoretical language to what we have in application. And let's say that as examples. Okay, so you have matrix A, which is going to consist of three rows and two columns, so this will be a 3 by 2 matrix. B, we have two rows and three columns, so this is going to be a 2 by 3 matrix. And we have with C, we have two rows, one column, so C would be a 2 by 1 matrix. Now let's say that if I'm multiplying the matrices A and B in the form of A times B, so looking at what we have here, so if I'm determining the product of the arrangement where we have A times B, so we have A at 2, 3, 0, 1, negative 4, 7. And going column by column, we have with matrix B, we have negative 1, 2, 1, 1, negative 2, negative 3. And now for the nature of the product, okay, what's going to happen here is that if the product is going to exist, then the number of columns in the first matrix and the number of rows in the second matrix must be the same. Okay, so here we have a 3 by 2 multiplying a 2 by 3. So we have the same between the number of columns in the first matrix and the number of rows in the second. And the resulting product will be the formation where we have the number of rows in the first matrix and the number of columns in the second. So we're going to have a 3 by 3 product. And taking what we have with A times B, okay, so you have these two matrices being multiplied. And if I go section by section, kind of taking what we had with vector equations, okay, so if I have AB1, so I have like matrix A times the first column of B1, which we have at negative 1, 1, and treat those like we had like x of 1, x of 2. We have x1 times the first column from the first matrix plus x of 2 times the second column from the first matrix. So here we have negative 1 over 2, 0, negative 4. And we have plus 1 over 3, 1, 7. And combining, okay, we have what's going to be negative 2 plus 3, 0 plus 1. And we have 4 plus 7. And we have for AB1, this will be 1, 1, and 11. And now for AB2, okay, so I have, again, matrix A. You have, this time we have with B2, you have the second column, so you have 2, negative 2. Running through the same kind of operation. I think of 2 as like x of 1 over the first column. Negative 2 is x of 2 over the second column. Again, just like what we had with the vector equations. And for this output, we have negative 2, and negative 22. And with one more column to work with from matrix B, so we have A times B of 3. Okay, so you have matrix A, same numbers, and we have third column from B, we have 1, negative 3, and again, you have 1 over the first column from A, and you have plus negative 3 over the second column from A, and just combining, okay, the output we have at negative 7, negative 3, and negative 25. And since all columns of B are now used up, okay, we have with A times B, okay, you have taking the product, okay, and so you have AB1, AB2, AB3, and assimilating the elements and making into the combined product. Okay, we have 1, -2, -7, 1, -2, -3, and we have the last row in the product. We have 11, -22, and -25. Now, if I were to reverse the order, okay, so I have not A times B, but B times A. So in this case, you have B is a 2 by 3 matrix, A is a 3 by 2. Here we had the same number between the amount of columns that we have in the first matrix, which we now have at B, and the number of rows in the second matrix, which we now have at A. And the resulting product, okay, will be a 2 by 2. Okay, so you have a 2 by 2 matrix. Okay, so situating what we have here. Okay, so you have BA1, BA2, so you have all of B, multiplying the first column of A, and again treating what we have with 2, 0, -4, all of these as weight. So you have 2 over the first column from B plus 0 times the second column from B, and we have plus -4 times the last column from B, and just combining. Okay, so we come out to, let's say you have -2 plus 0 plus -4, so we have it -6. And the bottom number we have 2 plus 0 plus 12, which will be at 14. So B times A of 1 comes out to -6, 14. And we have with the second and last column from matrix A to work with, and being multiplied by B. Okay, so you have 3 over the first column, 1 over the second column, 7 over the last, and just taking the product of the top numbers as well as the bottom numbers. You have like -3 plus 2 plus 7, which would be at 6, and we have 3 plus -2, which is 1, and we have plus -21, so this will come out to -20. And so just putting together what we have here, we have -6, 14 for the first column, 6, -20 for the second. All right, and looking at multiplying what we have with, say, A times C. Okay, so we have A is a 3 by 2 matrix. C, we have a 2 by 1. And again, we have number of columns in A, number of rows in C will be the same. Outside numbers, okay, will define the dimensions of the resulting product. So this would be a 3 by 1. So we have with A times C. So 3 and -1 is weight. So you have 3 over 2, 0, 4, and -1 over 3, 1, 7. So you have 6 plus -3 is 3. And you have 0 plus -1 is -1. And you have -12 plus -7, which will be -19. So you had the resulting output to be at 3, -1, and -19. And if I have C times A, okay, so we have C is a 2 by 1, A is a 3 by 2. Notice we have the number of columns in C and the number of rows in A to be a mismatch. So 1 is not equal to 3. And since we don't have an identity, there is going to be no resulting solution. Now, in the case of what's going to be the transpose of a matrix, and this is where you're going to have a switch around, okay, between the number of rows and columns. Okay, and just so you have given an M by N matrix A, the transpose of A is going to be the N by M matrix denoted by A of T. Okay, so you have A is equal to 1, 2. Okay, you have 2 by 1 matrix, and the transpose is going to be a 1 by 2, where in this case, okay, you have in this case the transpose is going to be at 1, 2. And for B, okay, we have given a 2 by 3 matrix. The transpose BT is going to be a 3 by 2. So we have first column becomes first row and vice versa. So you have 1, 4, 2, 5, 3, 6. And say we have with C, you have a 3 by 4 matrix, and the transpose is going to be a 4 by 3. So you have like, say for instance, you have the first row in C, and the transpose is going to be the elements in the first column, and second row leads the transpose to second column, last row, last column, same elements. Now regarding operations among transposes, and say if you have let A and B denote matrices whose sizes are appropriate for the following sums and products. Okay, so you have the transpose of A, this will come out to A. And where we have operations to exist, okay, we have for the transpose of the sums of or the transpose of the sum of matrices A and B, this will come out to the sum of the transposes of A and B. And for any scalar R, okay, you have, okay, for the transpose of the product of R and A, this will be equal to R times the transpose of A. And for the transpose of the product of A and B, this would translate out to the product of the transpose of B times the transpose of A. All right, now just samples of working with transposes. Okay, so you have three given matrices. And we have A, we have the given 3 by 2 matrix. B, we have 2 by 3 matrix with the numbers. And C, we have another 3 by 2 matrix. And if we're looking for the transpose of the product of A and B, okay, so you have, so just going with the property, okay, so you have A times B, okay, and taking the transpose of this, so you're looking at transpose of B times that of A. And now for the transpose of A, okay, so you're going to have going column by column, we have 2, 3, 0, 1, negative 4, 7. For the transpose of B, okay, you have, in this case, okay, row formation changes over to column formation and vice versa. So you have negative 1, 2, 1, 1, negative 2, negative 3. And now for the for what we have in the formation, now the transpose is going to end up being a 3 by 3 matrix. And if we put this in terms of like what we had again with the vector equation, okay, so if we have, okay, so again, we're looking at the transpose of B, and let's say we had the first column from the transpose of A. So again, we have in the setup, treating the 2 and the 3 as weights. We have in the product, you have 2 times the first column from the transpose of B, plus 3 times the second column from the transpose of B, and the output you have 1, negative 2, negative 7. And if we follow through, transpose of B times the transpose of the second column of A. So in this case, we have 0 and 1 from the second column of the transpose of A. And again, just going through the formation, we have that output to be 1, negative 2, negative 3. And then shifting over to the last column from the transpose of A, while working with the transpose of B. Okay, so again, this time we have negative 4 as the first weight, 7 as the second, and we have with the output, we have 11, negative 22, and negative 25. And so we have in the overall result, okay, just putting the elements all together. And again, the product is going to be a 3 by 3 matrix. So for the transpose of the product of A times B, we have first row we have 1, 1, 11. Second row we have negative 2, negative 2, negative 22. Last row we have negative 7, negative 3, and negative 25. And in the case of operations, okay, now if I'm looking for the transpose of the sum of A and C, again we have A consisting of 2, 3, 0, 1, negative 4, 7, going row by row. And also going row by row, we have C to consist of 3, 0, negative 1, 1, and 2, 4. And for the transpose of A, again, first row becomes first column, second row, second column, third row becomes the third column. And likewise with C, we have 3, 0, negative 1, 1, 2, 4. If we go, again, column by column. And so for the transpose of the sum of A and C, this will be equal to the sum of the transposes of A and C. And we have to be able to add these elements together. Okay, the matrices must be the same, and it turns out that both of these are 2 by 3 matrices, and adding the corresponding position portions. Okay, so you have 2 plus 3 is 5, 0, negative 1 is minus 1, negative 4 plus 2 is negative 2, and 3 plus 0 is 3, 1 plus 1 is 2, 7 plus 4 is 11. So we have 5, negative 1, negative 2, 3, 2, and 11 for the final output.